Quantum numbers. Quantum numbers are used to describe the location of electrons in an atom. An electron can only occupy specific energy levels. These energy levels are numbered, starting with 1 and corresponding to higher integers. So our first quantum number that we want to deal with is called our principal quantum number. The principal quantum number corresponds to the energy levels 1, 2, 3, up through n that are calculated from a hydrogen atom. So the principal quantum number designates the energy level or the distance away from the nucleus electrons are found. And the greatest number of electrons in any given energy level is 2n squared. An energy level is actually made up of many energy states that are closely grouped together. So our next quantum number is called our angular momentum quantum number. And our angular momentum quantum number is referred to as the states as sublevels. The L quantum number describes the sublevels within an energy level. The number of energy levels for each, the number of sublevels for each energy level equals the value of the principal quantum number for that level. And the angular momentum quantum number designates the shape of that sublevel. So if L equals 0, we're looking at an s orbital. And an s orbital is a spherical orbital. So down along the bottom, we have 1s, 2s, and 3s. We're looking at spherical orbitals that are getting bigger as we go from the first energy level to the second energy level to the third energy level. Up along the top, we're looking at a cross-section through those orbitals, and what we see, the shaded regions are where the electrons are most likely to be found, and those colorless regions called nodes are the places within that orbital where electrons are least likely to be found. If L equals 1, we're talking about a p orbital, and a p orbital is found along 3 different axes, x, y, and z. If L equals 2, we're looking at a d orbital, which has 5 different orientations in space. And if L equals 3, we're looking at an f orbital, which has 7 orientations in space. There's 1 sublevel for the first energy level, 2 sublevels for the second energy level, 3 sublevels for the third energy level, and so forth. The lowest sublevel in each level has been named S, and for this, L is designated with a value of 0. The second sublevel is named P with an L value of 1. The third sublevel is D with an L value of 2. The fourth is F with an L value of 3. So, the first energy level has only an s orbital. The second energy level has an s and a p orbital. The third has an sp and d orbital, and so forth. Aufbau's principle says that as protons are added one by one to the nucleus to build up the elements, electrons are added one by one to the orbitals. So if we've got the first energy level, there's an s sublevel. Second energy level has an s and a p sublevel. The third has an SPD sublevel. The fourth has an SPD and F sublevel. 5 has SPDF. 6 is SPDF. And 7 is SPDF. Now electrons are going to fill these sublevels from lowest to highest energy. So it's not necessarily an entire energy level that's filled before the next. To figure out the order in which sublevels are filled, we're going to take this flowchart and add arrows, and they're going to be diagonal. So 1s is filled first, followed by 2s, followed by 2p3s, 3p4s, 3d4p5s, 4d 5p, 6s, and so forth down our flowchart. So this will enable us to determine which sublevels are filled with electrons first, from lowest energy to highest energy. Now we have what's called our magnetic quantum number. And we're going to designate this with an m sub L. And it's related to the orientation of the orbital in space. So we saw that our s orbital has one orientation in space, and we're going to designate that with the magnetic quantum number of 0. If we look at a p sublevel, there are 3 orientations in space. So our magnetic quantum number, or our m sub L number, will be -1, 0, +1. D has 5 orientations in space. So our m sub L values will be -2, -1, 0, +1, +2. And our F has 7 orientations in space. So -3, -2, -1, 0, +1, +2, +3. And those values relate to the orientation of the orbital in space, which is referred to as our magnetic quantum number. Now we have what's referred to as Hunds Rule. And Hunds Rule says the lowest energy configuration for an atom is the one having the maximum number of unpaired electrons in a particular set of orbitals. And we have what's called the Pauli exclusion principle. And it states that an orbital can only hold 2 electrons. And these electrons must be spinning in opposite directions within the orbital because they will be repelling each other. So let's see what we're dealing with. We have our S, P, D, and F sublevels. We've got the orientations within space, and now let's fill electrons. So if we have electrons filling our s orbital, we can have 2 electrons in each orbital. So our first electron would be an arrow up, and our second would be an arrow down, one spinning in the up direction, one spinning in the down direction. Now if we look at the p orbital, our electrons are going to go into our orbitals singly first because they repel each other. And then once each of those orbitals within the p sublevel have 1 electron, then the electrons will have to pair up. And again, the electrons are going to be spinning in opposite directions, and we're going to designate them with our arrows, one going up and one going down. The same thing would happen in our D and our F sublevels, where the electrons would fill the individual orbitals first with 1 electron and then pair up secondly. So this leads us to our last quantum number, called our magnetic spin quantum number. It's designated with an m sub s, and the values we would use for this are +1/2 and -1/2. We're going to have our electrons spinning in the up or the down direction. If it's spinning up, we're going to designate it with an m sub s of +1. If it's spinning down, we're going to designate it with an m sub s of -1. So quantum numbers. First we have our principal quantum number. Okay, we're going to use our variable n to stand for the principal quantum number, and that tells us the size and the energy level. Angular momentum quantum number, which we're designating with an L, is related to the shape of the atomic orbital. Our magnetic quantum number, m sub L, is the orientation of that orbital. And our electron spin quantum number, m sub s, is the spin of the electrons. So if we wanted to summarize our quantum numbers, the first thing we would designate is our principal quantum number. So we've got n equals 1, 2, 3, 4, and so on. From there, we've got our angular momentum quantum number, 0, 0, 1, 0, 1, 2, 0, 1, 2, 3. The orbital notation, if we're in the first energy level and the L value of 0, would be a 1s orbital designation. 2, 0 for our quantum numbers would be 2s. 2, 1 would be 2p. 3, 0 would have an orbital designation of 3s. 3, 1 would be an orbital designation of 3p. 3, 2 would be an orbital designation of 3d, and so forth. When we look at our magnetic quantum number, we're looking at the orientation in space, so we've got 0, 0, minus 1, 0, plus 1, 0, minus 1, 0, plus 1, minus 2, minus 1, 0, plus 1, plus 2, and so forth. The number of orbitals, we would have 1 orbital in our 1s. We would have 1 plus 3, or 4 orbitals in our 2. We would have 1 plus 3 plus 5 in our third energy level. And we'd have a 1, 3, 5, and 7 in our fourth energy level.